In organic chemistry, two of the really key skills that you need to be able to do is to identify isomers of organic compounds, so different structures of the same molecular formula, and you need to be able to name them. And you need to be able to name things whether they've got isomers or not. So that's called nomenclature. You see that fancy word, it just means naming. That's all it means. And as someone said yesterday very astutely, why don't we just call it naming? Okay, we will, but I'll put that word there because you might see it in your exams. Okay, that's the only reason I'll leave it there. And your future university lecturers will probably use it too. I've got a couple of little tricks for remembering how to name organic compounds. I'm going to start just with naming things with a functional group that are what we call straight chains. There's no bits coming off them. Alright? Now I'm going to start by looking at, sorry, brain just quickly failed on me there. I'm going to start by looking at a 4-carbon alcohol. So if you do want to make these with molecular models while I'm going through, that might be a good idea. Remember, they won't look exactly the same as what I write because yours is in 3 dimensions and I've only got 2 dimensions to play with. So I'm going to do expanded, condensed structural formula for these. So if I was going to have a 4-carbon alcohol, then I should know from last year that for every carbon, I have 2n plus 1 hydrogens, and somewhere I have the OH functional group. So this is what we call a general formula. And I remember these because it's really good for if I'm asked to write or draw and name all of the isomers of, in this case, butanol, then I can do that. So the most obvious one would be to put all the carbons in line, which is going to be 4, and it's going to be 9, okay, this 9, hydrogens, and then OH there. So I'm going to put all of my carbons like ducks in a row. And I'm going to put the OH group on the end like it's showing here. Then I've got to fill in those spaces with hydrogens. Now you're going to put bonds on those. I'm just going to abbreviate it. So CH3, CH2, because I've already got 2 carbon-carbon bonds, so I've got room for 2 more. CH2, CH2. Now to name this, I need to know a few things. First of all, how many carbons? There's 4. So I must remember my prefixes. Meth for 1, eth for 2, prop for 3, bute for 4, and then it just becomes the same as a shape. So pent, like a pentagon, for 5. Hex, like a hexagon, for 6, and so on. If you want a little mnemonic to remember the first 4, the one I tend to use in my mind is must eat peanut butter. Okay? Nice easy one to remember. Meth, eth, prop, bute. This has got meth, eth, prop, bute. It's got 4 carbons. So that's my thing I have to consider. But the very first thing I do is I actually check what functional group or functional groups are present. And I can see this OH, and I know that this functional group is called an alcohol, and alcohols end in OL. That's the end of the word. Then I do my count, 1, 2, 3, 4, and I'm going to do it both ways. 1, 2, 3, 4, 1, 2, 3, 4. 4 is bute, so it must be butanol. Then my next thing is to go, is there anywhere else that functional group can go? So could it go somewhere else and make a different compound? Yes, it could. I could put it on this carbon or this carbon and it would be a different chemical. If the answer is yes, then I have to use a number. Well, it's either on the number 1 carbon or the number 4. So which one do I choose? I choose the number 1 because it is the lower number. The main functional group in this is the alcohol, not the alkane carbon chain. The main functional group is the alcohol. So the carbon that is on gets the lowest number. So this is 1-butanol or butan-1-ol. I find it easier to call it 1-butanol though, because as you've probably just observed, I'm actually writing the name backwards. I write the names of organic compounds backwards. By the way, I do the same thing if I was to draw this from the name. So I know that 2-butanol exists, so I'm going to show you what I mean by that. There is a thing called 2-butanol. Alright? So, I kind of don't do this exactly backwards. But what I do is I go, the biggest giveaway on a name is the number of carbons. So the first thing I'm going to start with is the but. Butane, not butene or butine, so I know that the and means there's only single bonds in there. So what I do is I go, oh, okay, so there's 4 carbons in a row. So I'll do that. 1, 2, 3, 4. Then I go, oh, it's got an OH, because it's got O. And this number tells me it's on the number 2. So what I probably had to do here is go 1, 2, 3, 4, 1, 2, 3, 4. So I can choose whichever way I want to build it. Because the O is on number 2, so that's what 2 something or other O means, then I put my OH on one of my 2 carbons that have got number 2 next to them. Then I start filling it in with hydrogens, because there's nothing else in that name. Be careful of this carbon here. So many times that people go, oh, it's CH3, CH2, CH2, CH3. Careful, it's already got the OH on it, so it's only got room for one more hydrogen. CH2, CH3. Okay. So these are what we call structural isomers. By the way, this is quite a cool one. This one here has got what we call optical isomers. If you were to make it and look at it in 3 dimensions, it would look, if I look at this carbon here, which is what we call a chiral carbon, or an asymmetric carbon, it would look a bit like this. One thing is going to be sticking straight up. 2 bits will be coming out towards you, and that's what these little triangles mean. They're sticking out like that. And then if you have it like that, it'll probably be 1 coming towards me. Alright? And if I make this one, and I just arbitrarily choose what I'm going to put there, then you might make a different one for the person next to you. You might make that one, whereas the person next to you might have those 2 groups swapped. And actually you'll find that they aren't superimposable. You can't just put one on top of the other and they're the same. These are called optical isomers, and they're really cool if you're interested in living systems. Proteins, sugars, all those sorts of things have what we call optical isomers. And the way that the protein works, if you didn't have the correct optical isomer, then it wouldn't work. It had a different 3-dimensional shape, and so it wouldn't work properly. They're really cool things. These aren't chiral carbon. We're going to learn more about those later though. Okay, so that's our first bit of naming, is just moving the functional group around. The second thing that can happen in isomerism, and sticking with this context, is I might move a carbon around. So I might say, is there somewhere else I can put a carbon, but keep the OH at that end group, at that end one? So I'm going to rip off that first CH3. So I've ripped that off. Is there somewhere else I can put that first carbon that will not just make it a straight chain? Well, if I stick it up here, it's still, even though it looks jagged, it's still what we call a straight chain. It's the same thing. So I can't put it here. That's a no-go. But if I was to put it here, it makes what we call a branched chain compound. So if I was to put a CH3 up here, I can put the alcohol on that one before. Then I've created a new compound. So he'll have CH3, CH, because we've already got 3 carbon bonds, and CH2. You'll notice it's still got 9 hydrogens plus the OH, so it's still got the same general formula. Again, naming this, it's a good idea to go backwards. Oh, I can see an OH. It must end in O. The largest carbon chain has got 3 carbons on it. Whichever way you look at it, it's 3 carbons. Either of those red lines show you the path of the largest carbon chain. I'm going to go for the straight one because it's easier for my brain to get around more than anything. So I'm going to number it. 1, 2, 3, 1, 2, 3. 3 carbons meet a prop. So this is actually a type of propanol. The alcohol is on carbon 3 or number 1, so I choose 1 because that's the lowest number that I can put the functional group on. So it's a 1 propanol. But there's something else happening. There's this other carbon up the top. Okay? That one there is what we call a side chain. And side chains end in -ile. So methyl, ethyl, propyl, depending on the size of them. That side chain is made up of 1 carbon, so met. So it's methyl. Now, here's my next thing. I know it's on carbon 2 because both of those numbers agree with that, but also I've now chosen this numbering. But actually, if I put that anywhere else, would it make a different compound? If I put it there, well, it makes butanol, so that's different. If I put it there, what does it do? It actually makes it the same as this one. It just doesn't quite look like that. But here's my hint to you for exams. If you're not sure, put the number with it. I'm going to put this in brackets because it is correct without it, but it's also correct with it. This is methyl 1-propanol, but it's also 2-methyl 1-propanol. So if you're unsure, chuck the number in, would be my advice. There is one more isomer of these things, of this, okay, and, sorry, not got the, yes there is, where we've got those 2 carbons are actually there, alright? So that would be 2-methyl 2-propanol. I'm not going to call that one up, I'm sure you can do that on your own. Now the other, just very quickly, the other type of isomerism you're likely to meet that needs to be named happens with a double bond. So I'm just going to very quickly show you that with but-2-ene. So ene means a double bond. But means that it's got 4 carbons, but actually the Germans will twice for a good reason. If I put those 4 carbons across this, then there are 2 ways I can do it. Clear enough for you. If I'm going to choose the carbon chain, it's the way that I always think of this. If I look at the carbon chain, here the carbon chain is going like that. Okay, so it's going, making basically the letter C if you can get 90 degrees and be a little bit creative. Okay. Here the carbon chain goes across the double bond, or transits the double bond. Okay. So if you think of transit as going across something, or from one place to another, go from this place to this place, you have to go through the double bond, like a transit lounge as it were, then that helps with naming. These are called geometric isomers. While they have the same structural formula, they have the same molecular formula, they actually have different geometry. So this is also an example of a geometric isomer. It's a special one called an enantiomer, or optical isomer. This one here is just geometric isomers called cis-trans. You might see Z's and E's when you're looking things up online. That's because Z is German for, stands for the German meaning of it, which is zusammen, which means together. That's a Z. And entgegen, which means opposite, are opposite. Okay. So you might see that. They are sometimes called E and they are sometimes called Z, but for your purposes, this is called a cis isomer, and this is called a trans isomer. So this would be called cis-2-butene. That's on the screen. This would be called trans-2-butene. Right. As we go through the unit, I'll show you how to name the particular groups, because some of them get a bit funky. Particularly amines, because we've got secondary and tertiary amines. They're really cool. Really, I think it's fun to name, but it's a little bit of a geek. So, there's the general rules though for naming. Naming backwards tends to be the easiest way, which means identifying the functional group first, then identifying the longest carbon chain, then identifying the position of the functional group. If you've got a side chain, same idea, but what added to that sequence is, are there any side chains that I haven't accounted for? or in this case BL. Number that the same way as you numbered the functional group. So once I've said that that's a 1 alcohol, that has to be carbon number 2, and that has to be carbon number 3. No choice. Be aware that you might come across optical isomerism, again we'll go through that more later. And be aware that if we're looking at alkenes, there is what we call cis-trans or geometric isomerism.